So here's the actual experiment. I have connected the signal generator to the input of the core of the NR-2 circuit, and so this is the signal generator cable, goes to the input and it continues, and it ends up in channel 1 in the scope. I'm using this signal from the signal generator to trigger the scope, so the scope will always stay where this signal from the signal generator lies here. And then I'm using the output of the NR2 and going to the channel 2 of the scope. And both channels of the scope are set for 20 millivolts peak to peak, so the same value. And when I switch on the power supply, you will see the second signal, this one, which is the signal that is coming out of the NR2. And the first signal is the one that triggers the scope, and it's the signal of the signal generator. So I have set now the signal generator to about 8 megahertz, and let's do the test, the first test. So here's the amplitude potentiometer, and here's the phase potentiometer, and I have a little switch here that sets the sensitivity of the NR2. So let's do the test now, and what I'm going to do is I'm going to take the phase and adjust it and adjust the amplitude. All right, so I'm going to put some markers here so we can have a clue how much. Yeah, let's use the X1 marker. So our signal basically is now at around this point of the X1 marker. So we need to vary the phase of the signal and put the other end, this top end, to put it here. Okay. Now if we move this end here, we'll have 360 degrees of phase shift. So this is what we are going to do now. We're going to shift the phase slowly, and of course the amplitude changes as the phase changes. So we're going to compensate with the amplitude potentiometer here, and we're shifting the phase even more, compensate for the amplitude, shifting the phase. So here we go, 360 degrees of phase difference. And we have some overlap too, if we want. Quite a few overlap here. Okay, so let's go back in our original phase here. Here we go. So let's try another frequency now. Let's try 18 megahertz. So we have to put the horizontal, okay, a little bit, the timing, and let's see which one is the phase. Okay, this one is the phase. So I have to put a marker again to this one. Move the amplitude a little bit so they match. Okay, and now we're gonna we're gonna shift the signal 360 degrees at 18 megahertz. So here we go, and compensate for the amplitude. Right? The controls are not touchy at all. I have used very good quality potentiometers, so there's no backlash or sticky grease on the potentiometers. They're very, very well adjustable to the sub-millimeter scale. So here we go, 360 degrees at 18 megahertz. Now let's go to 30 megahertz. Let me adjust the generator to 30 megahertz. So here we go, 30 megahertz, and let's adjust the timing a little bit. All right, which one is our phase? This one is our phase. So let's bring it down and put our marker right on spot, just about here, and try the same thing again to shift the phase and at the same time compensate for the amplitude difference so you can see this. So here you got it, right? Now let's go back. We have quite a lot of overlap in some bands, in some others not. So let's go back to let's go to 3.6 megahertz now. So I'm trying different frequencies actually here on the shortwave, so you can see the effect on different frequencies, and we have to compensate for the amplitude difference. All right, what we have here, we have a situation where the amplitude is even in its lower state, the lower setting of the potentiometer, the amplitude cannot be set lower than this. So in that case, we have to lower down the switch, the gain switch. Here we go. So we have minimum gain now, and we can compensate for this for the with the amplitude. So let's try the same thing again. Here's our output signal. Actually, let's make the horizontal a little bit better. And here's our output signal. All right. And let's try to move the phase, to shift the phase. So let's do it and compensate for the amplitude at the same time. All right, let's increase a little bit the gain. Now we want a little bit of more gain. Okay, here we go. 360 degrees out of phase shift. Right, and we have some overlap. Look at that, we have quite a lot of overlap. You see? So we have quite a lot of overlap here. So let's go to the very bottom end, the 1.6 megahertz, and try the same thing again. Which is the, oh, here we go. Let's bring this down, put the gain at low. Now the input signal here and from the generator is at 20 millivolts. So as you can see, there's no significant distortion here in the output signal. So this means that the NR-2 will be able to handle quite a lot of signal. Actually 20 millivolts peak to peak at 50 ohms. It's about S9 plus 40. So it's quite a lot of signal, and it has some overhead for more as well. So let's go here and set the phase. All right, and just about here. So we are marginally now at the very edge of the bands. So we need a little bit more gain antenna here. Okay, see lots of overlap here. Actually, let's do it from that end. All right, let's do it from that end so we can mark this end and change the phase differently. It doesn't matter actually. See, 360 degrees, more than that actually. Lots of overlap here. Okay, and I want to go back to the 3.6 megahertz because let me check once again. Let me put the marker here. Yeah, I think that will do it. So we are at 3.6 megahertz that we have tried before. And yes, that's the thing. Before I was trying from that end to shift it to that end, okay? And now I'm trying from that end to shift it to the other end. So that's clearly more than 360 degrees. And a bit of overlap here. So here you got it. The NR-2 working from 1.6 to all the way to 30 megahertz, and it's able to shift the phase at least 360 degrees, and the amplitude for from a few fractions of the millivolt up to about even half a volt peak to peak, depending on the band, and with an input signal of S9 plus 40, about 20 millivolts peak to peak. So this is a very successful experiment, and this is the basis for the NR-2. This is the core circuit of the NR-2 noise canceller that I'm going to build, and it's working really nice. The controls are not touchy at all, and I have lots of overhead for the phase, and for the amplitude lots of overlap, and three different levels of amplitude. And I can actually show you also this. If I go to the low level, I'm reaching a point where I can barely see this. So let me switch the second channel to 2 millivolts, let's say, per division. You can barely see. I can see here a small fluctuation through the noise. So, and I have measured that. I know that this outputs some signal that the scope cannot see, because I have moved the signal, this signal light here to a receiver. So, but it's too low. All right, and if I continue to increase the amplitude and switch the scale to higher scales, and I switch the gain to higher, switch the scale to higher, just to show you how much gain you can take out of this thing. Where am I? Oh, I was in the highest gain now. So here in this particular band, in the frequency, the 3.6 megahertz, I can vary the gain from where is it? Let me measure that again. Okay, this is 343 millivolts peak to peak. At 1 mega ohm, I'm using the 1 mega ohm ports here. So 43 millivolts peak to peak, all the way up to the sub millivolt range with a 20 millivolts of input signal. So there is lots and lots of headroom for compensating for the loss of the local antenna, the local noise antenna that the NR1 will use. And we can also very much attenuate this signal if our noise antenna has lots of gain, and we can amplify very much this antenna if our noise antenna doesn't have gain. It's very lossy. So there's lots of overhead here. So there you have it. The experiment is a success, and you can also use this for many other things. For example, you could use this as a block circuit to vary the phase for a quadrature oscillator. Instead of having an oscillator operating at 4 times the frequency, and divided down, square wave, dividing down with a 74 to 4 times less the frequency, so that you can have a quadrature oscillator. You can have a very nice sine wave oscillator which operates at the frequency of your local oscillator. So you don't need actually this complexity. Anyway, I thought you find this experiment useful, so I'm continuing with the rest of the video.